Previously, we talked a little bit about mirrors and how when rays of light reflect off of them, they reflect in a way so the incoming angle is the same as the outcoming angle. But let's talk a little bit about what image is actually created when we have reflections. So we have here, let's call this line right down the middle a mirror. And these are our two objects. We have our blue star and our red star as our two objects. And so what sort of image is going to be created? Next time you look at a mirror, you can notice that depending on how close you are to the mirror, that can tell you how far away that image of yourself that you see in the mirror appears. And really what ends up happening is if you take the distance between whatever the object is and the mirror, and then you just take that same distance behind the mirror, that's where your object is going to show up on the other side. Oh, I guess that's a little bit too close. There we go. Let's move it out a little bit. There you go. So this image, or this object, is creating an image that is the same distance behind the mirror. It's the same thing for our red star. It's going to be the same distance just behind the mirror. So what does that mean about the pathway that the light is going to take when we see the reflection? So let's create another object here, and let's call that object the observer. So if our observer is down here, this circle, and we want to figure out what is the path of the rays that allow the observer to see these objects, the first thing we want to do is look at what is the straight line between the observer and each of the objects. Let's start with the red star. If we draw a straight line from our observer to the red star, it's going to look a little bit something like this. And if we do the same thing for the blue star, it's going to look like this. Now, because there's this mirror in the middle, and because we're not actually having light rays that penetrate through the mirror and see some imaginary object on the other side of the mirror, I'm going to make these lines here dashed lines. Because really, these are imaginary rays that we can use to kind of understand what we're seeing, but that's not what the light is actually doing. What we remember, if we remember from last time, what light actually does is it's going to bounce back at the same angle that it hits the wall. So if we do that, we see something like this for the red star and something like this for the blue star. So as you can see, we use this imaginary ray here to figure out we use this imaginary ray here to figure out where the observer is going to be getting the light from, where the light is going to be hitting from the object it's going to hit the mirror, and then we just draw that line back to the observer. But we line it up with this imaginary image on the other side of the mirror. So this is how we figure out what the light rays are actually doing so we can see each of these objects. Now, let's imagine a scenario where instead of our observer being down at the bottom, let's get rid of all this, we put our observer up here at the top. So let's say this is our observer. Now, if we're looking at the red object, we just do the exact same thing we were doing. We draw a straight line between our observer and our red object, and then we make this line dotted because there's not actual light that's going there, and then instead we draw the line to our red object. But if we're looking at what happens with the blue object, let's line this up and draw our line to the blue object. And then we can see that actually our blue object, our light ray to the blue object doesn't pass through the mirror because the mirror stops right here. So what that means is we, from this angle, cannot see the blue object in the mirror because there's no light ray that is going to pass from our observer through the mirror to bounce off of to the other object. So even though it looks like we might be able to see this imaginary object, because the light rays do not interact with the mirror, we really just can't. So from this angle, we could only see the red star, not the blue star. So all of that was dealing with a plane mirror. And when we say plane, we don't mean like plain bagel, like a boring thing, but no, plane as in like a plane in geometry, like a flat plane. So that was dealing with a plane mirror. But now what happens if we bend the mirror a little bit? So there's actually two different types of bent mirrors that we can think of. Now here we have a concave mirror, and to remember the word concave, you can think about the fact that if you have a cave, like you're living in a cave, that's like an indentation in a rock. And so a concave mirror is going to look a little bit like a cave. Like you could imagine a little Neanderthal or something just hanging out in here. And the rain's coming down on him, but he's just happy because he's in his cave and he is not getting wet. So that is how we think of concave mirrors. And then convex is the opposite of that. This is a type of mirror that is going to be curved outwards. So it's just the opposite of concave. Now, because each of these types of mirrors is going to be reflecting light rays based on their normal, let's draw the normal ray from each of the incoming light rays. See, it's right there, and then it curves a little bit. Each of these normals for the convex mirror is slightly more curved than the last. And they're all curving outside as you move around the mirror. So that's why all of these light rays end up going away and scattering when you have a convex mirror. It's because all of those normal lines are curving away. If we do a similar thing here for the concave mirror, we can see that all of the normal lines, they curve inward as they're going along. So that's why all of the light rays are focused in at this point right here. So concave mirrors, the normal lines are pointing inwards, and so all of the waves, all of the light rays come in and get focused. Convex, all of the normal lines are pointing outwards, so all of the light rays come in and scatter after they hit that mirror. Let's take a moment and switch gears and start talking about refraction instead of reflection. Now, if anybody has gone to a restaurant and ordered a drink and they get their glass of water, and here's your glass of water, and this is the level where the water is at, and you get a straw in it, and your straw comes in something like this. That's a really bad looking straw. Your straw comes in something like this. If you look at it, it's going to seem to almost bend and go through the water at a different point. Almost like it's a different angle going through the water. This is caused by refraction. But really what refraction is it's a measure of what is the speed of light through an object. So the equation that we use to figure out what the speed of light through an object is uses something called the index of refraction. So here we have three different materials. So we have air, so we're just going to say that this is air, that has an index of refraction of 1. We have our blue material that has an index of refraction of 2, and we have our red material that has an index of refraction of 1.5. Now, you can notice right off the bat that all of our index of refractions are greater than 1. And that's going to actually be a general rule about the index of refraction. N is always going to be greater than 1. So let's talk about how we can figure out what the speed of light is through each of these three medium. Index of refraction, if anybody else has heard about an index before in physics or any other sort of science, an index usually means that there is some sort of ratio going on or multiple terms that are being aggregated together. And here we have a ratio. So the index of refraction, N, is something that we're going to calculate by taking c, the speed of light, divided by v, the speed of light through whatever that object is. So when we say that c is the speed of light, what we really mean is that c is the speed of light through a vacuum. even though technically it's the speed of light in a vacuum, people for shorthand just say c is the speed of light. And that's represented as, well, it's not represented, it is calculated to be 3 times 10 to the 8th meters per second. So this value, 3 times 10 to the 8 meters per second, I'm sure you all have heard something about how it's a pretty special value, like E equals mc squared. That equation, that c there, the c part, that comes from the speed of light. So it's a really important quantity, and the most important thing that we're going to talk about is the fact that nothing can travel faster than the speed of light. So you can't find a substance that light travels faster through. And this is why we cannot have an n that is less than 1. If n was less than 1, let's say we had an n of 0.5, and we solve this equation over here on the left, we end up with a velocity through our substance with this n of 1/2 greater than the speed of light. So this is why our n has to be greater than 1. So let's do some calculations to figure out what exactly the speed of the what is the speed of light through each of these three substances. So when we have an n of 1, that's pretty easy. We end up dividing c by 1, and v is going to be equal to c divided by 1, which equals c. Over here for an n of 2, v is equal to c divided by 2, so we end up with 1.5 times 10 to the 8th. And then over here, for the third substance, we have v is equal to c divided by 1.5, which equals 2 times 10 to the 8th. These are both in meters per second. Meters per second. So let's look at what actually happens when we have a light ray traveling through our objects. Let's start with a light ray that comes in at a pretty shallow angle. So it's going to be coming in over here from the left. Now, when we reach our object, we want to look at what our normal line looks like, because our normal line is going to tell us how the light ray bends. So because we're going from a low index of refraction, 1, to a higher index of refraction, 2, we're going to be bending towards the normal line. And over here for our second substance, we want to look again at where that normal line is to see how we're going to be bending. Because we're going from a high 2 to a lower index of refraction, 1.5, we're going to bend away from the normal line, but it's not going to be quite as shallow as this initial angle. So it's going to be something like this. And then, as we go from 1.5 back to 1, we're going to we're going to re-hit this same angle, because we're going back to the same medium and through the same index of refraction. So here, we're going to have this same angle. So we go from a low index of refraction to a high index of refraction, and when we do that, we have a sharp turn. We go to a slightly lower index of refraction, so it's a slight curve away from the normal, and then when we go back to our original substance, we curve back and go to that same angle. So this is what is happening with refraction. Next, we're going to talk about diffraction. Now, reflection and refraction were two things that were commonly associated with light rays. I mean, reflection can happen with sound waves or other physical waves, but refraction is something that only happens with light waves, and reflection is just a lot easier to see with light waves. However, diffraction is something that occurs with any type of wave. Basically what diffraction is it's the spreading out of a wave after it passes through a barrier. So here in this setup that I've drawn, these lines represent the amplitude or the highest peak of some waves that are approaching a barrier. And so they're coming in and they are spread out. They're nice long waves like this. They're traveling in. And then they reach this barrier, and they're going to pass through this barrier. And some people may think that the waves are just going to come through just this short little line. It's going to become this little ray, and all of these other rays are going to just bounce back. But that's not exactly what happens. Yes, these other waves bounce back, but what actually ends up happening through this hole is that we have these waves that come through and start to spread out. So immediately after, yeah, they're going to kind of look like these flat waves, but then they're going to kind of start to spread out. And they create this almost like Wi-Fi, almost, like the symbol for Wi-Fi, or, it starts to create this sort of pattern. This is why when you have, let's say, a closed door, or maybe a door that's cracked open a little bit, you don't just hear sound right in front of that crack, but it kind of spreads out as it passes through the doorway. That's because of diffraction. Now, the interesting thing about diffraction is that the amount that this spreads out is dependent on the wavelength of the incoming wave. So right here, we see that the wavelength is about 2 centimeters, maybe just a centimeter long, and our opening is about the same size. And so we see diffraction. If our wavelengths were super, super close together, so if our wave looked like this, coming in really, really close together, then we wouldn't see diffraction because the wavelength was way smaller than the hole. So the hole that is causing the diffraction needs to only be 1 or 2 times bigger than the wavelength for us to see this diffraction pattern. This gets really interesting with light because light has tiny, tiny, tiny wavelengths. So in order to see diffraction with light, you need a tiny, tiny, tiny hole.